Hi students, in the last classes we were discussing about the Sakata model. Then after that we reached to eightfold way, then finally to the Quark model and also the confined quarks. These are the topics that we discussed in the last class. Now we are going to the experimental evidence for the Quarks model. After that we will discuss about the colors, then the quantum chromodynamics, and finally we will discuss about the gluons as well. So the Quark model, it is successfully explained the success of SU3 mechanism, and also the Quark model provided a mechanism explaining the connection between resonances and semi-stable particles. It also made it possible to calculate the magnetic moments of various hadrons and also to predict the results of interaction between particles. For example, according to the Quark model, the ratio between the probability of interaction between nucleons and a target compared with that of a pions and the same target should tend to 3 by 2 at higher energies, because according to the model, at high energies the probability of interaction should be proportional to the number of quarks and antiquarks in the particle. So here I took an example of nucleon as proton. As you know, the proton, it is having three quarks, that is UUD. Okay, it is shown here. So here you have three quarks, and in the case of a pion, the pion, it is UD bar. Okay, it is having one quark and a anti-quark. Okay, now according to the Quark model, at high energies the probability of interaction should be proportional to the number of quarks. So in the case of a interaction between a nucleon, here it is a proton and a target, that is proportional to the number of quarks. Here the number of quarks is 3. And the second case, you have the pions. The pions having one quark and an anti-quark. So here the probability of interaction is proportional to 2. So if you take the ratio between the probability of interaction between this proton and the pion, that is equal to 3 by 2, and this ratio, it was indeed experimentally verified. So this is an experimental evidence for the Quarks model. Now we will look for the second experimental evidence. The products of the pion-proton interaction, you will get a pairs of muons. Okay, when the bombarding pions were negative, then 4 times as many muons pairs were formed than when the pions were positive. That is, if you are interacting a proton with a pi minus, and then you are interacting a proton with a pi plus, then the muon pairs that is formed, that is 4 times greater than in the case of proton with a pi plus. So what is the reason? Okay, and how you can explain it? that we are going to discuss. Okay, so the muons are produced by annihilation of a quark in the proton and an anti-quark in the pion. Okay, so here the protons contains no anti-quarks. Okay, that is, this is a proton is having quarks only UUD. Okay, so one thing is, if you make a collision of proton with a proton, you cannot find, or there is the formation of muon pairs in this process is very rare, because the reason you need the annihilation of a quark and an anti-quark to get the muons. Okay, so the chance or the probability of formation of muon pairs by the collision of proton-proton is very rare. Now we will come back to our pion-proton interaction. I already told the ratio of 4:1 between the muon formation rate from the pi minus interact with the proton and pi plus interact with the proton collision. This is explained by a basic rule. Okay, the basic rule is, according to this rule, or according to this, the probability of high energy annihilation is proportional to the sum of squares of the electric charges. So in the collision of a positive pion, that is pi plus, it is having the quarks U d bar with a proton having quarks UUD. Okay, the annihilation involves a d in the proton and a d bar in the pion. Okay, and whose charges are minus 1 by 3 and plus 1 by 3. Okay, for the d quark, it is having the charge minus 1 by 3, and anti-quarks of d, that is d bar, it is having charge plus 1 by 3. So the probability of annihilation is proportional to 2 by 9. How it comes? By the basic rule, the probability of high energy annihilation is proportional to the sum of squares of the electric charges. So for the d quark, it is having charge minus 1 by 3. So you have to take minus 1 by 3 square, and for the d bar, the electric charge is 1 by 3. So again you have to add it 1 by 3 all square. So minus 1 by 3 all square plus 1 by 3 all square, that will give you 2 by 9. Now we will go to the negative pion interacting with the proton, and in this process, or in this interaction, the annihilation involves U and U bar. Okay, so here when you are taking the negative pion is pi minus, that is having quarks U bar d. So here the annihilation involves U from the proton and U bar from the negative pion. So the charges. The charges of U and U bar are 2 by 3 and minus 2 by 3. So the probability as per the basic rule is 2 by 3 all square plus minus 2 by 3 all square, that will give you 8 by 9. Now the ratio of probabilities, you can take 8 by 9 is to 2 by 9, that is nothing but 4:1, and this is exactly found experimentally. So this is another experimental evidence for the Quark model. So after the Quark model was introduced by Delman and Z, the physicists pointed out that under this model, 2 or 3 quarks in a hadron could be in the same state. That is having identical sets of quantum numbers in the same state. For example, if you are taking the omega minus, according to the Quark model, it is having quarks SSS. And the analysis of the properties of that particle which possesses spin 3 by 2 shows that all 3 quarks have parallel spins and 0 orbital angular momentum. Similarly, the particles like delta plus plus and delta minus, they are regarded as the ground state of the quark combinations UUU and DDD. That is, delta plus plus having the quarks UUU in the ground state and delta minus having the quarks DDD as the ground state. Okay, so these 3 quarks have parallel spins and are in identical physical states. So these particles, that is omega minus, delta plus plus, delta minus, these are having identical 3 quarks and have the parallel spin. Okay, and since these quarks have spin half, they are fermions, and one would expect them to obey the Pauli exclusion principle. So here there is a violation of Pauli's exclusion principle. So this made a threat for the Quark model initially. Then faced with this dilemma, physicists had several options. One option was to assume that quarks do not obey Pauli principle, and it was suggested by Greenberg, and he suggested quarks obey new para-Fermi statistics, allowing any 3 quarks to have the same quantum number. Then another explanation was suggested by 2 physicists at the University of Chicago, Nambu and Han. According to this explanation, the quarks do obey the Pauli principle, but they possesses an additional quantum number which can have 3 different values for each quarks. The additional quantum number characterizing the quarks was arbitrarily named color, and each quark possesses an additional quantum number and which can have 3 different values for each quark. For example, if you are taking the omega minus, so it is having 3 quarks, 3 s quarks. They are identical in all the familiar quantum numbers like strangeness, electric charge, spin, etc. But they are differ with respect to the new quantum number. Okay, so here, so the 3 values of the colors are red, yellow and blue. Okay, you may find in another version of the colors of the quarks as red, white and blue, but we will just focus on this red, yellow and blue. Okay, so I took the example of omega minus. So in the case of omega minus, you have three S quarks. So these three S quarks are red S, yellow S, and a blue S. Okay, so instead of just saying SSS, we will just say we have one red S quark, one yellow S quark, and a blue S quark. So I told, according to this theory, each quark assigned red, yellow, and blue color, whereas each anti-quarks are assigned opposite colors, that is anti-red, anti-yellow, anti-blue. Okay. Another thing is, a combination of the three different colors is colorless or white. And another important principle of the color model is that all mesons and baryons are always colorless. Basically, all the hadrons, they are colorless. So, we can say the three quarks in a baryons are always of three different colors. Then only you will get a colorless combination. Okay. And in the case of mesons, the quark and anti-quarks are of two opposite colors, so that the mesons too are mesons also get a colorless combination. Okay, and all the observable particles are colorless. The color, unlike other quantum number, cannot serve as a basis for classifying the hadrons, nor has it as a direct influence on interaction between them. Now we will go to quantum chromodynamics and gluons. Basically, the notion of color was originally introduced quite arbitrarily to explain what appeared to be a contradiction to the Pauli's exclusion principle. However, in due course, it has proved very useful to other aspects of the Quark theory as well. According to the current theory of the strong force, the color is the source of the inter-quark strong force. Okay, so the force between particles possessing color has been named the chromodynamic force, and the theory of color is called the quantum chromodynamics. So you can say the force between the quarks in the hadron originates in the color. In other words, the color is the source of the inter-quark strong force, and this is mathematically analogous to the unitary spin charges. There is also a real analogy to the electric charge being the source of the electromagnetic force. The concept of color explains why the force acting between quarks is so different in character from the force between the hadrons. The really strong force acts only between colored particles, whereas the hadrons are colorless. The theory assumes that the chromodynamic force is transmitted by 8 electrically neutral particles of zero mass and spin 1, and these particles are called gluons. And each gluon carries a combination of a color and an anti-color. Okay. The gluons in some way resembles the photons, which transmits the electromagnetic force, but unlike the photon, which has no electric charge, the gluons do have color. So here, like unlike the photons doesn't have any electric charge, but here the gluons have a color. Okay, so more precisely, each gluon carries a combination of a color and an anti-color. Being themselves colored, the gluons exert chromodynamic forces on each other, and this explains their ability to serve as a string binding the quarks and to cause the force to increase as the separation between the quarks increases. Okay. So in each process of emission or absorption of a gluon, the color of the quark may change depending on the color and anti-color carried by the gluon. For example, when a blue U quark emits a gluon carrying the blue and anti-red color, it becomes a red U quark that I have shown in the bottom. Okay, so that is, you have a blue U quark and it is emitting a gluon with blue and anti-red. So your blue U quark transfer to a red U quark. Now this emitted gluon is absorbed by a red D quark. Let us assume like that. Then what will happen? This red D quarks become a blue D quark. Okay. So this is a way how the gluons are emitting and transmitting, and how the quarks are changing. Okay. Now there are 6 color changing gluons. That is, one is GRB bar, GRY bar, GBR bar, GBY bar, GYR bar, GYB bar. Okay, this represents, first one is GRB bar, means this gluon is having red and anti-blue. GRY bar is gluon with red color and anti-yellow. Then GBR bar is gluon with blue and anti-red. Next one is blue anti-yellow, then yellow anti-red, then yellow anti-blue, like this way. And two color preserving gluons, that is, it is simply denoted by G0 and G0 prime, actually which can be regarded as carrying combinations of colors and their anti-colors, and will be denoted like this, G0 and G0 prime. So the transmission of the chromodynamic force by exchanging gluons causes the quarks in the hadron to change color continually. So one example I will show here. For example, if you take a pi plus meson, so it is having quarks U and D bar. So it was with the U with red color and D bar with anti-red color. Now by exchange of a gluon GRB bar, what will happen? The U, red colored U become blue colored U, and anti-red colored D bar become anti-blue colored D bar. Then again a emission of GYB bar by D bar quark. Then what will happen? This D bar with the anti-blue color become D bar with anti-yellow color, and at the same time this GYV bar is absorbed by the U quark with blue color, that become u quark with yellow color. Okay, now again, if this u bar is this u quark is emitting a G0. G0 is a color preserving gluon, so there won't be any change because the uy bar was the just uh, sorry uy was the u quark with yellow color was the existing one, so it just continue as such. And similarly, by absorbing that G0, your D bar quark with anti-yellow, that just preserve as such. Now in the last, you can see if this D bar with anti-yellow, that is emitting a GBY bar, then what will happen? This D bar with anti-yellow become D bar with anti-blue. At the same time, absorbing that gluon by the U quark, the U yellow colored quark become U blue colored quark, like that. This continuously happening. Okay, so anyway, some gluon exchange will be between these two quarks. Okay, or there is always a chromodynamic force between these two quarks. That is the case of a pion. And when we comes to a proton, it is having UUD. So here you can see initially your first U quark was red colored, second U quark was blue colored, and third D quark was yellow colored. So there is an exchange of gluon between U and U. So that exchanging gluon is GRB bar. So what will happen? This U quarks just change its colors. Okay, so red colored U quark become blue colored U quark, and this blue colored U quark become red colored U quark, like that. Then another emission of gluon by this middle U quark to the D quark emission, or you can say the exchange of chromodynamic force. Okay, so you can see, you just look at it and you can understand the basics of this quantum chromodynamics and the chromodynamic forces between the quarks in the mesons, or in the proton, or you can see so many examples are available. You just go and read it, and you understand the basics and the fundamentals of this quantum chromodynamics. Okay, at present, quantum chromodynamics appears to provide a good description of the real strong interaction that occurs between the quarks themselves. And I will go to a small topic that we mentioned during our classes, even though it is not in our syllabus. I will just tell you about the SU2 and SU3. You have already studied these topics, I think, in mathematical physics 2. Okay, so we were discussing about SU2 and SU3 symmetries. So here the SU2, we have up quark and D quark form a isospin doublet. So this will give you 3 generators. Okay, because you have 2 members, so the number of generators is n square minus 1, so that is 3. So we will have our in the SU2 symmetry or SU2 flavors, you have 2 quark states U, that is the up quark with state 1 0, and down quark with state 0 1. Okay, so the generators of this SU2 are the Pauli matrices, and in the case of SU3 you have isospin triplets, and this will give you 8 generators, and these generators are Gell-Mann matrices. Okay, so this I have shown here: lambda 1, lambda 2, lambda 3, lambda 4, like that up to lambda 8. Okay, now what you have to see is we already discussed about the multipliers and super multipliers. So we were discussing about when you are discussing about the multiplets, you have singlet, or you may have octet or decouplets, like that. So these all the things are well explained by our SU3 and SU2 mechanism. So these topics you can learn it more perfect way by just looking at the mathematical physics books. Okay, uh, from the group theory you will get almost all the details and how the things are splitting. This three multiplies of 3 into 3 into 3, that will give you a singlet plus a octet plus octet plus a decouplets. Okay, so actually from these combinations you will get what are the totally symmetric, what are the mixed symmetric and totally anti-symmetric combinations and all. I will just attach one PDF in our Moodle, and you can read it out. These are very interesting topics, and also along with this SU2 and SU3 symmetries, you can also look at these things by another method that is called the Young tabulex. So if you just those who are interested, they only need to look at it. Okay, by looking the Young tabulex, you will understand all these combinations and all predictions, and also the different multipliers, how the super multipliers are forming. All these things are coming mathematically, and these are the beauty of our physics. Okay, the theoretical things are just coming through the simple mathematics, not the simple mathematics. Mathematics, these are little bit complex, so you can just look at it and study very well. Okay, but still you have to understand something about the SU2 and SU3 symmetries and their generators and all those things.